Well, they'll talk anyway. There you go.
You're on.
Might manage without for this.
You might not need it.
How can everybody hear me just like this?
No.
In that case, let's put you on a stand.
So if you're going to be standing up to the whole thing.
Don't speak too close into it either. So condense the mic. So
You're blocking part of the screen. You have to move way to the side here.
If you get back far enough, we can see your
There you
silhouette.
go. Right.
Okay, so welcome everybody. I have to manage a little bit with the room here. Manage distance to the website notice. We're going to talk about SAM a bit more in detail, and especially about fusion in this case. Not cold fusion, but hot fusion that we all know about. We all see the periodic table here. We've seen some examples during the conference, especially from Sapphire. And I want to focus on this fusion field because we feel it's extremely important, the things that we find in the structured error model. Just to show everybody, this is the periodic table. And the elements that we're about to talk about is, let's see, there's uranium, right there, 92. We're going to talk about tungsten, and we're going to talk about a whole bunch of lighter elements. Now why I put this up already is to point out that if you talk about transmutations from uranium, and you find things over here in this row or the row above, everybody I think can intuitively already understand there's a big transmutation going on there. That's a big puzzle. Many experiments with cold fusion fields and other experiments as well. We see those steps, so they have to be explained. Whether it goes upward in the periodic table, meaning building fusion, so we have lighter elements. That is what we've been talking about already. And they will become heavier elements. That's the creation process. On the other hand, we have a destruction process. Nature has both, just like life. We grow, we die. James, can you put the second slide up? So I think everybody has seen the graph already before, but it's an extremely important one. So I want to zoom in just a little bit and explain a little bit more. In the beginning here, and I hope you can see as well. In the very beginning, we're talking about hydrogen and a couple of hydrogen isotopes. Hydrogen 1, hydrogen 2, hydrogen 3, or deuterium and tritium. These over here, it's not very visible, I understand, but you can see that the accuracy is almost 100%, but especially in the beginning there is a little bit deviation. I'm not going to talk about that. There are explanations for that I do want to point out. The next step is about number 11 here. This is just about carbon. You see a very linear, straight linear line here. Please keep that in mind. That means the correlation is pretty much dead on.
What's the vertical axis?
The correlation is between the binding energy calculated by SAM purely on the structure and compared to the literal binding energy values. So again,
What is binding energy?
binding energy. The nucleons in the nucleus are sticking together. It's a big topic, many talk about that. Probably Philip Hatt will be talking about that a little bit as well. This is what keeps the nucleons together, so what we call the protons. How do they stay together? We say through the electrons. But there's a certain amount of energy related to that. In our model and in reality, every proton-proton connection, literally two balls together, is 2.225 mega electron volt. It's a pretty high number. So it's about 1,000,000 times of the normal chemistry level, which deals with electron volts, maybe a little bit more. So we're talking about huge energy. This is nuclear fission energy. Then I want to point out that there are jumps. We'll get back to that later, maybe in the debate setting, in the discussion setting. I want to invite you later on to shoot any question you want. But they are important. So we have a nice linear piece here and a huge jump. Note that it is also from the official values. Nobody explains that, nobody talks about that. These jumps, so imagine we have the beginning of that little curve and the ending of that curve, and we take the whole bunch and we move them a little bit to the right. So we increase some virtual data points, if you will. Now we get a nice linear curve. What that would imply is that there are other elements possibly there. Other constructions. We do not know everything that is out there. What would happen if you were to implement a virtual data point, you would force the line to be much more linear. Then, what we see here also, just about, 65, we see that the lines start to deviate. This is the crucial part. We've shown here, in this correlation, that it holds true for just about half the periodic table. Spot on. You can see it also in the accuracy. We're talking about 99.5 or higher percent accuracy. So we believe that this shows that the structure is the correct structure. Then we see them deviating, and that needs to be explained. We all know about nuclear fusion, and there's a whole lot of energy coming from it. And we're all looking for that energy that is hiding in the atom. That's a prevalent thought for the past century or so. We believe that we can explain it, and I will try to zoom in on that with some calculations and examples. And James, can you go to the next slide, please?
Yeah, just a second. So just to clarify, binding energy according to our model is that if you imagine you have a deuteron, you have two protons stuck together, that's one line. And if you get a tetrahedron, you count the proton-to-proton connections, and those are each called a line. So there are four lines. Six lines here in a tetrahedron. So we multiply the 6 times the 2.25 megaelectron volts. And as you get into different structures, the number of lines jumps, and there's some jumps in the number of lines, and that's what we're seeing, these jumps on the red line, is that the number of lines jumps instead of a steady linear progression.
Okay. Next slide. Just to point this one out, this is the delta energy, meaning the difference. So the first data point is the difference between element 1 and element 2, in this case hydrogen and deuterium. The next data point, the second data point, is between deuterium and tritium, so helium 2, helium 3, hydrogen 2, hydrogen 3. So we took the difference between that and compared them again. So the red here is, I need to read myself. The red is the structure binding energy, and the blue is the literature binding energy. And we can see again that later on they start to deviate more. But in the beginning, when one goes up, the other one goes up just about as much. When it goes down, the other one goes down. So we believe that this is again a very good correlation. Okay, next slide. We have shown this slide before, a little bit changed. We see uranium on the left, 235, and we see the two fission products that come of it. Now this is merely an example. There are many, many combinations, and pretty much statistical spreading. However, as we know, and this is not explained at all properly, there are two huge peaks here, while the normal standard deviation you would expect one normal peak. This is a big enigma as well. Nobody can really explain it. We see an example here. Uranium-236 goes into xenon 140 and strontium 94 and 2 neutrons, which keeps the chain reaction going. The reason I pointed it out is because in the next slide we're going to try and compare it with some data that we've seen here on the conference.
So even though we have nuclear reactors and we've bombed a few countries and things like that, we really don't understand how the atom splits in fission, and we don't understand why it doesn't split in half. And we're seeing that it typically will split somewhere around 90, and again at 134, but half at 115 is the dip in this curve. And that's what they really can't explain, is why do they get these why doesn't it split in half?
And because of that, then and there, you already understand there must be a structure underneath that causes this, whatever that may be. Next slide. So yesterday evening we sat around here just before the campfire, and we started talking about some results in transmutations. And we thought, okay, let's see what we can do with the structured atom model. Can it help us explain these things? So we did a very quick and dirty calculus, very quick and dirty. We said, first we started off with tungsten, because tungsten is not only in sapphire mentioned a lot, but in other experiments as well. So it's a nice one. It's just about as heavy as gold, another nice correlation there. But it's an absolutely stable element, so why would it even split? Why would it change. So we took two of the heavier elements, and James, can you scoot back just a sec to the first page with the periodic table? It's just a few minutes. I'm going to point out tungsten here, number 74. And the elements that we come off, we go back here. So we go back from 74, 73, 72, all the way from this one over here, 71, all the way to the left. That's where we find with number 57 and 58, lanthanum and cerium. These two were pointed out, so we took the liberty to take these as an example.
Well, they came from Sapphire. The results that they presented at the results presented at the conference were that cerium and lanthanum were found, along with some other unnamed elements and things like that. And the reason we're working with tungsten is we're making an assumption here, in that they had an interesting meltdown of a tungsten probe. So we're thinking maybe they experimented with tungsten. So this is an assumption.
Big one. The point is here that the change is pretty big. We're talking about a lot of nucleons coming off. So there must be an explanation for that. Let's see if we can find at least some of that. Yeah, let's go back to the other pages. Next one. No, keep. So the quick calculus would be 1A2, that's the number of nucleons, the number of protons in the nucleus. So tungsten has 182, and in the case of lanthanum 193, in the case of cerium 136. So we simply deduct those, and we're left off with the rest. And if you identify those, number 43 is calcium, and number 46 is titanium. These two, I believe, were mentioned in the results presented by Sapphire. What I want to point out is to the next slide, please, James. Next one. Go back to the uranium first. Yeah. The nucleus branches, I'm going to try and point it out. The red ones are basically at the end of branches, or antlers if you will. That's where the activity is, but they're branching. And some of these branches snap off. That is our belief. So we have a rigid structure, and some of these branches literally snap off, and those are the fission products. There's something else happening. You can see the nucleus here. This one is pretty roundish, pretty spherical. Not entirely, a little bit flattened, but spherical. We see the other two. This has been a big question in the beginning when we were creating these. It seems that the nucleus is actually elongated, or pear-shaped, if you will. Now there's a reason for that, a big important reason. The thing is that the branches show the stress energy. And the stress energy, as we call it, is that deviation between the blue and the red line. That, we believe, is the nuclear energy that is hiding in the atom. That is why fission is possible. That's the energy that's stored. And we can also deduce from that graph that only starts to happen just about halfway the periodic table, or as everybody knows, iron at the top. At the beginning, in the lighter elements, we fuse all the way up to iron, but if we have really heavy elements, they go back to iron. So what does nature do? Nature does not like stress. So it breaks them down if it can. What does it break down? And here's the power of the structured atom. We understand now that these groups, these white groups and these light blue groups, those are the carbon nucleates explained at the presentations. They do want to make as much distance as possible. They don't want to see each other that much. So it starts to become elongated, a bit of a row-like. But it cannot do that infinitively because it would be too long and it starts to break up. So there's many things are already at play here in the nucleus, which we definitely do not understand all of them. But the thing is, if you can see, so this red one over here is the red one over there. So that's pretty much the same. And the structure you see here fits exactly in this, minus a group on the top, minus a group here on the bottom, and minus a group here on the left bottom.
That's the elements.
Yeah, what are the elements on the right?
These elements, I believe I took the xenon and the strontium. Xenon and strontium. But, as I mentioned, you can imagine all kinds of combinations, right? So, xenon, strontium, those two come off. Now, it can be that one uranium decays into this one, plus a whole bunch of those breaking off branches. And or those branches that snap off, because they are already so close, they cannot stay in the original nucleus, they break off, but they're already so close, they fuse back together. So now we see the complexity immediately occurring. There's fission and fusion going on in the same reaction, flow. They can change. The reason that those break off, especially those in the top here, in the bottom here, is because we already found in our binding energy data that they show the most stress energy. They are the most difficult to create. They are the rare earth elements. The rare earth elements show the most stress already. So to create them, the normal binding energy is simply there. That's the blue curvature we show with our structure. That's why it's too high between brackets. But if we start fissioning this in nuclear reactions, which one will break off first? Of course, the one with the most stress energy. The rest is just fine. That means the central branches, they snap off. This we can all confirm with data, but this is an ad hoc presentation, so it's a bit difficult now, and there are about 1,000 isotopes, so we need to create them all before we can do all. The thing is, this structure fits in there, and the central branches, they snap off because they show the most stress energy. So let's do some calculations with this, because now we're talking, can we predict it? Can we actually calculate that?
So, just for those who are curious what he means by why does uranium split? And this is a big question in other atoms. There's another model where the nucleus, instead of being these branches, just a solid blob. And the physicist that came up with this model, one of his biggest questions is, how can a neutron hit that nucleus and break apart this solid blob? And he was really impressed that we have this tree structure, and so a neutron hits a branch and it snaps off a branch is much easier to imagine than you break a cube of nucleons apart. And he thought that was pretty cool.
Yeah, let's try the next page. We just quick in between, we see the elements here, tungsten on the left with a W, wolfram in other languages. We can see that there are 1, 2, 3, 4 stable elements. So later on, I hope you understand that it matters which isotope you use or which combination you use. You can actually get different results depending on the isotope that you start out with. And that goes for most elements. Not all of them. Lanthanum has only 1 stable. But in the case of cerium, we have 1, 2, 3, 4 already. So there's what James showed in his presentation. There are many variations there. It matters, that's what I wanted to show. Go to the next page, please. Okay. Let's start with tungsten. Let's start with our experiment right now. We have tungsten here, which already approaches uranium. It's already pretty heavy. What was it, 188 or something like that? 182. And uranium is 235, 236, so it approaches it already, and it has a lot of binding energy already. But these elements are utterly stable, they should not fission at all. Well, if we look at sapphire, we see these products coming off, and we see a tungsten product disappearing. So, what is going on? First clue is, yeah, these branches break off, so let's take a look there. The lanthanum we took, and the cerium we took. Projected here and projected here. I put a third one at the bottom because there may be many other combinations and possibilities of the main structure still remaining. And again, you see on the left here, this purplish, and this one here, and some over here, they were broken off again. So what happens is we have this, again, these central branches with the most stress energy, they snap off. So what happens? We get a tungsten, we go to a cerium, but there are also the remaining products, and those are the lighter elements that we can show here. So we took the liberty of showing some that sapphire had as well, and there are many more. This is just a collection. But the thing is, you can imagine that a carbon would basically fit right there, or an oxygen would maybe fit right there, or a sulfur maybe came up off the top branch, and again, the breaking products that come off can also fuse again. At least that's our suspicion. Yeah, so let's go to the next slide.
So, all of these elements were ones that were shown on the examples from Sapphire, and then there were some unnamed ones that We don't know what they were.
Well,
Secret.
it's utterly chaotic, that I can promise you. We've seen that those results in many experiments, and everybody's struggling to explain them. Let's do some calculations. On the left, again, the example of uranium. Now, I want to emphasize first, this is very quick and dirty. Like I said, we need to create all the proper isotopes first, and there are 1,000 or 1,500 or so of them at least. So this is approximate, but we do want to show the power of the model. In given time, we can do much, much better than precision calculations. Okay, uranium-236, I took two others in this case, neodymium and zirconium, and sure, normally there would be a few neutrons there. Leave them out of the equation just for now, for quick and easy. Binding energy. Uranium-236 has, according to SAM, only on the structure, 2,109 mega electron volts. Huge amount, total. The official value that everybody knows is 1783. So the delta here in fat, in bold, is 326. That's your delta. That's the energy that is, the potential energy that is hiding in the uranium atom. Potential. The stress energy. The branches pressing away from each other. Then we have the products, the neodymium, 1266 minus 1185, remaining 81. That still stays in that neodymium atom. So nothing happens with it, stress energy stays there. It's not released. Same thing for zirconium, that's only 11, it's already smaller. We do the math, we take the 326 minus those two that are still remaining, and we end up in this case with 234, it is not exactly precise, it's a bit less, I think it's 210 just about. Energy that is actually released in a nuclear reaction by splitting uranium. And this totally correlates with what are the known values. Let's go to tungsten. Same thing. Tungsten goes into number 1, lanthanum, or number 2, another option, cerium. When you do the math, which we already did, 43 calcium would match with the lanthanum, 46 titanium would match with the cerium. So very simple. Those two products, depending on which path you take of destruction. We do the math. 6026, 4095, total is 167 would be released. Potential again. There's some remainder. The lanthanum is a rare earth element, still has 73 MeV, still quite a bit. But the lower ones, they are all below iron. And we've already seen in the graph, below iron there's pretty much no difference. So, quick and dirty, we took 0. Could be 0.3, 0.2, something like that. We do the math, and we get a release of 94 mega electron volt in potential. I say in potential because, as Wallace, I believe, pointed out, in the case of nitrogen and CO, it is not that all the energy is released and all the energy is taken again. It's a slight difference, and somehow it can balance. It can, through resonance, through whatever, the energy is used for a migration of a part of the nucleus to the other one. It's a rebalancing, a reorganizing. So, we believe that if you were able to do this, you could potentially have stable elements, stable fission as well, and release energy. And that would be a very, very important thing. So here we have a couple of these elements that we've seen are boxed in red. Those numbers that I've been showing. So 1626 would be the structured atom model calculus, 1495 would be the official literature value. You can see them here. We have a long table of this for all the elements on our website, where you can find all this data. So this is all the data. We do this calculus, and we wanted to show you today what we think is happening potentially in projects like Sapphire, Cold Fusion Experiment, and God knows what else. The important thing here is that nuclear waste reduction was mentioned. I believe in that potential. If this is indeed true, and we can start splitting atoms that are stable, we can not only get a whole bunch of energy, but we can clean up all the nuclear products, and in the meantime make a bunch of energy from elements that are very abundant, from lead to palladium to tungsten and all the others in between. And I think No, one more thing. Nature goes towards iron. Nature wants to release the stress energy. And I want to emphasize that again. We can see this going on. Nature wants to grow towards iron through fusion and destroy back to iron through fission. This is my contribution today, and I hope you will have some questions or criticism or follow-up.
So we've been studying cold fusion a lot, and they're using palladium. They're thinking that they're taking the deuteron, which is 2 protons and an electron. They're combining 2 of those together, and they're creating helium, which is a fusion process. And so they've been looking for helium and looking for helium. But when we listen to their results, they start talking about, oh, we're finding copper, we're finding silver, we're finding all these other metals inside these. Once they started looking, I mean, initially they weren't even looking for these things. So they call it cold fusion. But we think very well that what they were doing actually, and they're beginning to think that themselves, is that they're actually doing fission of possibly the palladium into lighter elements rather than fusing the hydrogen into heavier elements. And in the process, this is a theory we're working on, is that the inner electrons, or what conventionally are called neutrons, remain the same. You end up with 2 or 3 or 4 pieces, but the number of inner electrons doesn't change, and that's why they don't see the radioactivity, and that's why there isn't a hole in Toronto right now.
About holes, speaking of holes, we've been privy to some stories in the cold fusion field. Pons and Fleischmann are the most known persons. Before they came out with their results, there was a report of an accident whereby their small electrode was left on over the weekend to charge and to continue running, because these experiments took a long time. You want to know that they are stable and all that. They came back on a Monday. The laboratory table had a big hole. It went through, small electrode, palladium extremely expensive, so they're really careful with that. And it went to the concrete floor, and there was a couple of feet hole in the concrete floor with a small electrode. You cannot do that with any type of chemical energy, not even near. Whether it's fission or fusion, it doesn't matter. We believe it's fission because it's an accident. It's a problem. It was explosive, it was chaotic, and there are more stories about that. But Kubre is a profound, prominent, I should say, researcher from New Zealand who is well known in the cold fusion community. I believe it was him who already lost actually a colleague due to these kinds of accidents. So what I'm trying to say is we have so many of these examples already, and these accidents, nobody can explain them. We feel pretty confident that it's actually fission we're talking about. So maybe the promise of cold fusion is not even that important. Maybe fission can make a huge comeback here. Maybe we can start learning that, to use that, and to safely use that, and to destroy the mess that we leave behind, the radioactive stuff in the process. Okay.
Pons and Fleischmann made a comment, well, we'll be able to find helium after they had already made their announcement, and people said, well, you should be finding helium if you're doing fusion. And they said, oh, no problem, we'll do that. And then they spent a whole bunch of time doing it, and they couldn't. And that's one of the reasons they were discredited, is because they made this claim about helium. And that would indicate fusion. But once again, they didn't really investigate looking for other elements to try to find the copper and the silver and these other metals that they're getting. And now that they're looking for them, they're finding quite a few of them. So, no, I'm good.
Questions? Remarks? Let's start it.
What does it mean for the interstellar medium that Monty mentioned in the comparison in his talk?
I think I already... Well,
Repeat the question.
Okay, what does it mean for the interstellar medium of the elements that were named in the presentation of Sapphire, where there were predominantly lighter elements like the calciums, titaniums, etc.? As I mentioned before, nature strives for this peak point of iron in the center. Can you put up that graph there just for a second? No, we don't have it. So nature does that. So my first intuition answering that question is nature will strive to release the stress energy. Now there are many additive processes going on up there. That's not my specialty. But I can imagine that nature in star-like environments, in nebula, with the electric currents and the magnetic fields and the what have you, that nature actually is capable of destroying the elements that are too heavy with the stress energy back to the elements which have basically no stress energy. But we also see the elements being created, so it's not always only hydrogen and helium. It's pretty much from hydrogen all the way up to iron and a little bit beyond that are all very feasible elements. Nature doesn't bother, has no problem with that. And they are more or less the terrestrial elements, so the common elements from calcium and magnesium, titanium, iron, etc. So what I believe is, I would actually be surprised if we saw other elements than that. Maybe that's a better answer. Okay, next.
Edo, you show this graph where you've got your calculated energy in the nuclei, and you show this increasing deviation of the measured energy in the nuclei. Obviously, those two lines are deviating. We know that the heavier and heavier the elements get, the less stable they are. Have you tried to find whether there's a relationship between that excess and some function of the half-life of those nuclei? So like the bigger the gap is, would they become less and less stable as can be measured by their decay rates?
It's an excellent question. I have a very long answer, so I'm going to try and keep it short. Can you bring out the periodic table, please? First slide. Lead. Where's lead? Here's lead, number 82. And bismuth also, but let's stick to the lead. That is the last stable element that that is not fissile. Right? Stable elements cannot do anything with it, except that some shoots them against each other. Hint. From that moment on, they become radioactive. We can see, can you bring up the uranium slide? It's a bit bigger. Oh, one back, yeah. Right here in the center, you can see these two very close. There's actually a little gap here, it's a little bit tilted, so it's still spatial distance, but not much. Not only that, there are 5 of these greenish here and 5 of these greenish there. Add 1 neutron, you end up with 11. And 11 is the carbon nuclide in the center. So we think that these branches can break off due to that collision point. This collision point is an actual collision point because the branches start to grow in each other, just like antlers can potentially grow in each other from the left and right. That's not good. They see each other way too well now. That means if we add 1 neutron, which is fission in uranium, these two start to interact. This collision point pretty much starts to happen just about the lead bismuth from that point on. Hence, all the elements above that are radioactive. Could you repeat your question?
Yeah, it's really it's a quantitative question, really, whether there's a relationship between that energy excess and the half-life of the nucleus.
So the point of this story that I just gave you is, beyond that we can see there's a collision going on, or they're way too close, and you can understand that if I add 1 more, it's a very quick reaction. We do have many other isotopes, including unstable isotopes, and there's definitely a relationship within the structure and the decay time. It's a bit intuitive, and I don't think I can convey that now because I have to go in so much detail then.
And you probably need as many nuclei as possible, I suppose, to get...
I can do it, but I really need a lot of time to point out many things. What I do want to say is, yes, there is a correlation with the decay time, so we can totally see, okay, this is a quick reaction. This one is semi-stable, and this one is pretty stable. We can definitely see that, but we haven't been able to deduce it in a nice calculus or a calculable decay time. Not that yet, but on an intuitive level, a bit more than that, we can totally say, okay, decay time is correlating here very much.
Yeah, I'm trying to understand the concept of the stress energy. So were you saying that if we ignore stress energy, if we ignore that tungsten going to lanthanum and other things would be predicted to not give off very much energy, but if you include the idea of stress energy, then that transition would give off more energy?
Can you reformulate this? I'm not sure I
Well,
understand.
Yeah, I'm not sure I understand either.
Well, keep going.
Is the stress energy that you're talking about, is that part of your model, and it's not part of how people usually think about nucleuses?
Stress energy is a term we use for simply for the lack of a better term. That's one. At first, I really didn't know what to expect. I plotted the data, and at first I had like 40 elements, pretty linear, so I was really happy there. And then started the deviation started to come. So I started to worry there, and then it really turned up. And then the worry turned around and wait a minute, hang on. This is important, because that's why I point out the first part of the graph. The correlation is true. We didn't change our logic. We didn't change the method of building. It does become much more complex. So what I'm trying to say is the binding energy is actually always there as we calculate. But it is diminished due to what we call the stress factor, or meaning we want to repel each other in those branches. So the binding energy is really there, I believe, as calculated, but the stress factor, the repelling forces, diminish that number. Hence we see in practicality that lower number. Or rather, if I want to break off that central branch, there's a push from the other branches to help put out that central branch. So that's why the deviation starts to arise.
Okay,
The more
you're going too
branching,
fast for me, so I don't, maybe we can talk about the deviation later, so I don't know if my stress energy question is separate from that, or...
So if you look at this one here, it's linear, and so this nuclide over here is not going to really see this nuclide over here because it's in a long line. But when you look at this one, you can see the branches are very close to, and they're all positive protons, and so they're going to be pushing against each other, and they're going to want to stay as far apart as possible. But you don't have that here, so it's a lower stress energy between the nuclides. And here you have a lot of stress because they're packed so close together.
Right, I got that
Okay.
part. I'll ask later, I don't want to take the time. Yeah.
Sure. Anybody else? Eugene?
Yeah, kind of related to the two previous questions. It's only my intuition, so think of it what you may, but I think that maybe you're getting this deviation because of inherent staticity of your model, because your model is inherently static, there's nothing going on in there, so bear with me. Maybe this, and again, maybe there are correlations with half-life, etc. Maybe they are caused by some dynamic aspect of the system. Maybe there is some internal motion in these nuclei. This is my idea. And just treating it from purely mechanical point of view, you're calculating currently just the potential energy of interaction of all those things, but maybe there's a kinetic part that is connected to their mutual motion. Maybe that's what you're missing. But in order to, again, maybe, but in order to kind of figure it all out, you would have to, I think, take a look at things like other, let's say, dynamic characteristics such as angular momentum or spin, or like multiple whatever distributions in the distribution of charge in the nucleus, etc. So maybe that would be a path for, I don't know, enhancing this model in some way.
You might be totally right. That's for starters. I don't think it's kinetic, as in movement, as in the old-fashioned thinking. We do believe absolutely it's static. However, you are spot on with there is dynamics going on. But we would say that it is the electrodynamics that's going on there. That could be a whole dynamic movement, circulation, etc. But that's where we look at the electro-engineers, if you will, to explain that. Also, because of the first part of the graph correlates purely, precisely, just about, I would argue, since we changed no logic whatsoever, that is not going on. There's no movement in that sense. But I grant there's much more going on than we know right now. That's for sure.
Just to add up, to reinforce my own point. Sure. So since these elements, these heavier elements are unstable, maybe there's more movement going on in there. That was my point, sort of.
Again, you can be totally right. we don't want to say this is the utter truth. Absolutely not. What we are very much aware of is that we understand this ourselves very poorly. But we can identify certain things, and that's the task here.
Yeah. I think the forces at that distance would be so powerful that it's unlikely that there's a great deal of jostling or movement.
I'm shoot me for it, but I'm a firm believer of the static atom model. And one remark on top of that, that does not mean nothing's happening, because the moment you change something, it will react, and it will react in such a way, which makes total sense, that it is self-organizing. The elements don't need our help to say I'm going to be this or that, or be stable or not stable. That's all pretty fixed, as we know. So that's one. And another one I would like to point out, which we are not seeing here and leaving totally out of the equation. I know you know this. There's outer electrons. And if you keep in mind the deuteron, which has been talked about a lot, so I hope you'll have that concept in your mind, that let's just say there's one, I'm going to show an orbit of one outer electron. In the center here there are deuterons. There are deuterons there, many. And each deuteron has one outer electron. If I, in a very simple concept, say, okay, this orbital from one side of the, can you show this one? So on the left side of the deuteron is where the outer electron connects, but also on the other side. First of all, there's your uncertainty principle. There's a path, where is it? Or maybe it's spread out, I do not know. But the thing is, what I'm trying to point out, there is a connection of an outer electron to those nucleus in the center. They want to go out, but the moment it goes out, there's the other electron from the other branch coming in. So that could be the stress factor also. It doesn't have to be the protons. Could be both. So what I'm saying is, yes, there is much more going on. You are correct. And the outer electrons are much more uncertain, so there could definitely be movement. Hence, I follow your logic there. So that's another thing that we basically do not take into account right now. What you know, what I refer to, is that if you take away from certain elements all outer electrons, a stable atom can suddenly become an unstable atom. No, almost nobody knows this, but this is a fact in physics. So outer electrons do play a role in the stability of the nucleus, and I would argue we can see that pretty clear here.
So we got, it's 3:05, one more question. Well, we got Neil in the back here.
Oh, excuse me, Neil.
Go.
I just wanted to be real quick there. I'm going to softball for you. You mentioned iron, obviously, to a great degree. Obviously, it concentrates magnetic fields. One of the great things about iron. Plus, it does seem to be prevalent not only in the sun, but also in our ocean floors, as it seems to be bubbling up everywhere. Do you think that that is one of those stable products, and why that might be occurring because of iron?
I think iron is the most dominant, well, one of the most predominant elements.
Is this happening inside our Earth as well? Is that what
Yeah, sure, absolutely. I can see it happening. Actually, I think that this is the predominant drive. So anywhere you go in nature, that would be the drive. I do see it happening in plasma environment. That's where I believe everything happens. Whether it's inside in a microplasma spheroid in an electrode or an entire star, that doesn't matter. That's the scalability. But so the charge level, if you will, the energy level is probably what dictates this. So think of, and this is a very simple concept, I'm not saying it's true, but if I elevate my ambient charge level, the central branches at a certain point start to come loose and break off because the energy is high enough to do that. If I were to elevate it, I would destroy the atom further. Something to that effect.
Yeah.
Is that satisfactory?
Oh, of course.
Cool.
Yeah. One more comment on it. So if your assumption is right, that this was done with tungsten, I can see that train of thought there, because last year the tungsten probe was evaporated. So if you want to repeat that, you would probably do something like laser anode with tungsten. And then, I mean, you also, if you remember, if you see those pictures of either zooming into the tungsten probe or zooming into the anode, this looked pretty similar. So I think it's really a good idea. And what it means, of course, is that you have a stable element and you add basically electricity, electromagnetism, add this energy. And this energy is just enough to break free, basically let that stress factor overturn everything else, and it breaks down. So this would be actually really be a clean way of do fission, and it means that it, of course, it happens in different intensity, probably all over the world, in every system, in a certain way. And it also explains, mind that number of 95, 94 MeV within the tungsten example, that actually now very clear why at 7% it already maxed out the thermal capacity of sapphire.
Right.
Hell, what? I mean, there was nuclear fission going on in that chamber.
If you look at the tungsten probe, that's simply what we're referring to of the tungsten probe that disappeared. That was last year or the year before, I can't remember exactly now.
Yeah.
But Monty or Michael, I'm not sure, they showed these results of these elements.
Yeah.
And they were again those lighter elements that we showed on that other slide, and that's all below iron. But if you have a tungsten probe and you see those kinds of elements, you're left with only one possible conclusion. The atom simply fractured in pieces. We're talking about how and why, etc. So, yeah.
Pretty cool.
And maybe it's a really good suggestion for Sapphire. Again, I don't want to be sitting on their chair, but maybe they can pick up on some clues here, as you suggested. Play with metals and anode and whatnot, lace it or make it of pure of it. Mizuno, I pointed out in Japan, has this nickel mesh. James talked about it. And they pretty much take the palladium, which is horribly expensive. They're really complaining about it. So they take the palladium and they rub it on the nickel, very, very thin. And they get that awesome result that I pointed out. So I would say you just gave Sapphire a nice clue there.
You probably already done it. That's my assumption.
Well, I don't know, but yeah.
Thank you very much.
Thank you for your attention.
Very good.